Picture this. You're an astronaut floating in the vast emptiness of space. Below you, or is it above, a swirling disk of light spins around absolute darkness. Stars behind it bend and twist like reflections in a funhouse mirror. Your heart races. You've just crossed an invisible line in space, and now there's no going back. Welcome to the event horizon of a black hole, and you're about to become cosmic spaghetti. Today, we're taking you on the most terrifying journey in the universe, a one-way trip into a black hole. We'll answer the question that's haunted scientists and stargazers alike. What actually happens when you fall into one of these cosmic monsters? Spoiler alert, it's far stranger than science fiction ever imagined. Chapter 1. Not a hole, but a monster. Before we plunge into the abyss, let's get one thing straight. A black hole isn't actually a hole. It's the complete opposite. It's a region of space packed with so much mass that it creates gravity so intense, nothing can escape it. Not spaceships, not particles, not even light itself. Think of it this way. Imagine cramming an entire mountain into the size of a grain of sand. That's the kind of mind-bending density we're talking about. When a massive star, about 20 times heavier than our sun, runs out of fuel, its core collapses in on itself in a catastrophic supernova explosion. What's left behind is a stellar mass black hole, typically weighing between 10 to 30 times our sun's mass. But that's just the beginning. Black holes come in different flavors. There are stellar mass black holes with event horizons just tens of kilometers across. Then, there are the supermassive giants lurking at the centers of galaxies, monsters weighing millions or even billions of times more than our sun. Take Sagittarius A star, the supermassive black hole at our Milky Way's center. It tips the scales at roughly 4 million solar masses. And if that's not impressive enough, the current heavyweight champion is TON 618, a beast clocking in at 66 billion solar masses. Now, here's the critical anatomy lesson. Every black hole has two key features. First, the event horizon, that invisible spherical boundary we mentioned. Cross it, and you're trapped forever. It's literally the point of no return. Second, at the very center lies the singularity, a point where all that mass is crushed into infinite density, and our laws of physics simply break down and scream for mercy. Chapter 2. When reality starts bending. All right, let's begin your descent. You're approaching the black hole from a safe distance, and the first thing you notice is wrong. Everything looks wrong. The stars behind the black hole aren't where they should be. Light from distant galaxies bends around the massive object, creating multiple ghost images of the same star. As you drift closer, you see a glowing accretion disk, a whirlpool of superheated gas and dust spiraling into the void. It glows brilliant white and orange from friction, reaching temperatures of millions of degrees. Around the edge of the darkness, a bright photon ring appears where light orbits the black hole before either escaping or falling in. But here's where things get really weird. Time itself starts playing tricks on you. Einstein's general relativity predicts that clocks run slower in stronger gravity. As you approach, your clock ticks normally from your perspective, but to your crewmates watching from a safe distance, you appear to be moving in slow motion. In one NASA simulation, an astronaut made a 6-hour orbit near a supermassive black hole. When they returned to their distant colleagues, their clock read 6 hours, but the faraway clocks had jumped ahead by 6 hours and 36 minutes. The Voyager was literally 36 minutes younger. This time, dilation gets more extreme the closer you get. To outside observers, you'll never actually reach the event horizon. You'll appear to slow down, freeze, and fade away as your light redshifts into invisibility. But from your perspective, you're falling continuously, and the universe outside is fast-forwarding, like a movie on high speed. Chapter 3. The Invisible Line of Doom. And then, you cross it. Here's the shocking truth. You don't feel anything special. There's no flash of light, no alarm bells, no cosmic welcome to your doom sign. The event horizon isn't a physical wall, it's just a mathematical boundary where the rules of escape change forever. But make no mistake, everything has changed. Once you're inside, all roads lead to one destination, the singularity at the center. Even if you fired your rockets at full thrust in the opposite direction, you'd still be pulled inward. From your perspective, you're still falling normally. You might even feel calm for a moment, but your crewmates watching from outside, they saw you freeze at the horizon, your image fading to a dark red smudge before vanishing completely. Any radio signals you try to send now get stretched to infinite wavelengths. Communication is impossible. You're cut off from the universe forever. Now, here's a crucial detail that determines how long you survive. What size black hole did you fall into? If you picked a stellar mass black hole, the kind formed from a collapsed star, you're in immediate trouble. These black holes have event horizons only tens of kilometers wide, creating incredibly steep gravity gradients. The difference in gravitational pull between your feet and your head near the horizon is astronomical. You'd be torn apart well before reaching the event horizon. But if you're falling into a supermassive black hole like Sagittarius A star, congratulations, you get to survive the crossing. As NASA scientists put it, if you have the choice, you want to fall into a supermassive black hole. Their event horizons span millions of kilometers, making the gravity gradient at the edge relatively gentle. You could cross the threshold with minimal stress, feeling almost nothing unusual at first. Chapter 4. Becoming cosmic pasta. But don't celebrate your survival just yet. As you continue falling deeper inside the supermassive black hole, the tidal forces begin building. And this is where things get truly nightmarish. Tidal forces arise because gravity pulls harder on whatever's closest to the black hole. Your feet are closer than your head, so they feel a stronger pull. At first it's subtle, a gentle stretching sensation, but it builds and builds and builds. This process has a name, and it was popularized by none other than Stephen Hawking himself: Spaghettification. Imagine being pulled like taffy. Your body stretches lengthwise while being squeezed from the sides. Every molecule, every atom in your body experiences this differential pull. Your bones elongate, your muscles tear, your DNA unravels. You're being transformed from a three-dimensional human into a one-dimensional strand of matter, a cosmic noodle falling toward oblivion. For a stellar mass black hole, this happens violently and quickly, long before you reach the center. For a supermassive black hole, you might float peacefully for precious seconds or even minutes after crossing the horizon before the stretching becomes unbearable. NASA simulations suggest that falling into a 4 million solar mass black hole like Sagittarius A star gives you only about 12 seconds from crossing the event horizon to reaching the singularity. 12 seconds. That's all the time you have left in the entire universe. Chapter 5. Where physics goes to die. As the tidal forces intensify to their deadly peak, you're approaching the singularity, that point of infinite density at the black hole's core, where our understanding of physics completely collapses. According to Einstein's general relativity, you'd be crushed into a single point of infinite density. Everything that makes you, your memories, your atoms, the very quarks inside your atoms, compressed into mathematical nothingness. But here's the mind-bending twist. Nobody actually knows what happens at the singularity. General relativity predicts its own breakdown at this point. Our equations spit out infinities and nonsense. And physicists hate infinities. They're usually a sign that we're missing something crucial. Enter quantum mechanics. Many scientists believe that quantum gravity effects must kick in before you reach the true singularity. Some theories suggest the core might be an ultra-dense Planck star instead of an actual point. String theory proposes black holes are fuzzballs, tangles of vibrating strings with no singularity at all. These ideas are fascinating, but remain purely speculative. We have no way to observe what's really inside. One thing's for certain, though. From your perspective, you'd be unaware of your destruction until it's over. The end comes swiftly, without warning. One moment you exist, the next you don't. Meanwhile, outside the black hole, the universe has moved on. To your crewmates, you never fell in at all. You just faded away at the edge, frozen in time forever. Chapter 6. The paradox that broke physics. This brings us to one of the deepest mysteries in modern physics, the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. But black holes seem to violate this rule. When you fall in, all the information that makes you you appears to vanish from the universe forever. Stephen Hawking added another layer to this puzzle in the 1970s when he discovered that black holes actually emit faint thermal radiation, now called Hawking radiation. This means black holes aren't entirely black. They slowly evaporate over astronomical timescales, eventually disappearing completely. But if the black hole evaporates, what happens to all the information that fell in? This paradox has driven physicists crazy for decades. Some propose the information is encoded in the Hawking radiation. Others suggest it's stored on the event horizon like a hologram. Still others claim our entire understanding needs revision. The truth is, we simply don't know yet. Black holes guard their secrets jealously. Chapter 7. Hollywood vs. Reality. Before we wrap up, let's address the elephant in the room. Hollywood's black holes. The 2014 film Interstellar features one of the most scientifically accurate black holes ever put on screen. The rotating black hole, Gargantua, was rendered using actual equations from Einstein's relativity, specifically the Kerr metric for spinning black holes. Physicist Kip Thorne consulted on the film, ensuring the gravitational lensing and time dilation effects were realistic. When characters spend hours on a planet near the black hole while decades pass for their colleague in orbit, that's real physics, not movie magic. But many science fiction depictions get things wrong. Contrary to popular belief, black holes don't suck like cosmic vacuum cleaners. As NASA clarifies, if our sun were magically replaced with a black hole of equal mass, Earth would continue orbiting exactly as before. We'd just freeze in the darkness. Another myth, black holes as portals or wormholes. In reality, falling into a black hole is a one-way trip to destruction, not a shortcut to another universe. No spacecraft can return once it crosses the event horizon. The laws of physics forbid it. Yet, surprisingly, science fiction often gets the weirdest parts right. The spaghettification, the time dilation, the frozen image at the horizon. These aren't exaggerations. They're precisely what Einstein's equations predict. So, there you have it. The complete journey from approaching a black hole to your inevitable annihilation at its core. Whether you choose a stellar mass black hole and die quickly, or a supermassive one and survive a few extra seconds, the ending is always the same: total destruction. These objects represent the universe at its most extreme, places where space warps, time breaks, and physics itself surrenders. We've actually photographed these monsters, and they look exactly as Einstein predicted over a century ago. So, here's the final question. Would you dare take the plunge into a black hole to solve physics' greatest mystery? Let us know in the comments. If you enjoyed this cosmic journey, smash that like button and subscribe for more mind-bending content that makes you go, whoa.